Hello navigators. In this lecture, we are going to talk about that how we can fix the FV scheme for buoyant pimple or buoyant pimple with radiation. Basically, whenever we use a compressible scheme, how we can fix the FV scheme such that the error that we have seen in case of pressure is low and the overall solution accuracy improves. Let's get started. Right now, if you see this particular solution that we have, you can see here that the error is high, as you might have seen in the other lecture where we discussed that how do we set up buoyant pimple foam. Clearly the error is high. Due to this, the error in temperature is also high and we see very different structure of the flow. Now what I'll do is I'll copy this particular folder. Here we'll just make changes to the FV scheme. Right now the FV scheme is straightforward. Everything that is here is default. We'll first make the changes here. Here we'll use a linear at upwind scheme. Linear upwind with grad u that is computed using this particular scheme. And similarly here we'll use a limited scheme, Gauss limited linear with this is a slope limiter. Let me also confirm whether this particular discretization is valid. This I'm getting this particular discretization from one of the tutorial that is present in OpenFOAM. Limited linear 1 and limited linear upwind. With this I'll use the same discretization for others as well, for this one as well as EKP. Now we'll see that whether the solution that we get using this particular discretization is better or not. For this we are still going to use Gauss linear, and here this one is good, this one is corrected, this works well with the non-orthogonal mesh. Now I'll run this. First I'll clean all the previous runs, so you can see there is nothing here, and run. So we'll wait for some time to finish just one write step of this. It has returned solution for one time. We can kill this and see whether there is any improvement or not. Clearly the improvement is not there, and here and there we see more error as well. The main source of error is this. We can ignore this safely. Clearly the error is in the gradient computation, and the gradient is computed for the pressure. Let's use better discretization, which is least squares. With least squares it is better, but it is computationally expensive. But if the accuracy is improved, then our time steps will also improve. Let's see how much time this will take to write the solution, and then whether the solution is improved or not. This one is, this is least square, not linear squared. Least squares. So probably it should be here, this one. Yeah. Now let's run again. So you can clearly see the amount of time it took to write this particular solution was very less, and we'll wait for some more time to let this finish more number of solutions here, and then we'll kill this. We'll keep this running for much longer time because we want to see what are the changes we observe when we use this buoyant pimple and where there is only convection, and we'll do the same changes to the buoyant pimple with the radiation, this one, and we'll also observe that what are the changes in the long term, because in the short term we did not observe any changes. So I'll let it run for 1 second. Let's wait. So it has almost finished till 0.95. 1 second completed. Let's observe the results. Clearly there is this sign that the pressure contour looks something which is close to the real solution. There are some vortex shedding that is going on. This happens so early because there is asymmetry due to convection, and in case of velocity also you can see this. So let's observe temperature, and I'll play this. So you can see how this part is hotter and this part is cooler. This is the reason for that is because this is the direction of gravity. Let's also observe this in case of velocity. This part looks a little bit weird, but that can be fixed by making a proper mesh. And let's also observe pressure. So pressure contour also looks fine. Let's now compare this particular simulation to the simulation when we add radiation. I have done the similar changes to the scheme in case of buoyant pimple foam with radiation. You can see here, this is a scheme. So Gauss linear upwind with grad u, there is least squares and various other, including this one. We have this new scheme which was added compared to when there is only convection. I'll also run this one for 1 second and then we'll observe some changes if any. So we'll wait. We have the solution for up to 1 second. I'll kill this and open. So the initial contour looks similar. Now I'll also open this one with the change. This one is a fixed one, and also let me translate this to negative 1.6. Now we know that the gravity is acting in the negative z direction, and this one is without radiation, the upper one is with radiation. You can see we have this one here which shows that this is with radiation. Now let's first observe only temperature. We'll make the temperature changes from 200 to 300. 300 does not look good, so say 400. 400 looks good. Now we'll play. There is some change here that you can see. A little bit of change can be observed. That could be due to radiation. This is different than this one. The upper one is with radiation, and here also there is some change. This particular vortex is not there. So clearly due to radiation, the transfer of heat to this particular portion is higher at this particular second. Now clearly due to radiation there was some changes that we observed. Now when we fix the scheme, we can clearly see the difference in the simulation when we have radiation and we do not have a radiation. This was just an example problem. You can apply this to your particular problem and see that how radiation affects your flow. Okay, with this we'll stop. Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.